Primary key partitioning answers one question cleanly: given a key, which partition holds the data? But real applications need to query data in more ways than just find me the record with this key. Find all cars with color red. Find all users in Berlin. Find all products with price under 0. These are secondary index queries, queries on fields other than the primary key. And secondary indexes are harder to partition than primary data because the secondary index value doesn't determine which partition the primary record lives on. Here's the core problem. Suppose your cars are partitioned by car ID. Car with ID 1234 lives on partition 2. It happens to be red. If you're building an index on color, where does the entry for red car 1234 live? It's not obvious, and the answer determines the performance characteristics of writes and reads in fundamentally different ways. The book describes two approaches, with names that are precise about where the index lives. Document partition secondary indexes, also called local indexes, keep the secondary index collocated with the partition. Each partition maintains its own index covering only the records in that partition. Partition 2 has an index saying red cars in partition 2, IDs 1234, 5678. Partition 5 has an index saying red cars in partition 5, IDs 9012. The indexes are local, partial, and independent. Term partition secondary indexes, also called global indexes, maintain a single index covering all partitions, but the index itself is partitioned. Rather than each partition indexing its own records, there's a global index of all red cars, partition 2 IDs 1234, 5678, partition 5 IDs 9012 with the global index partitioned by the index term. These two approaches make the opposite trade-offs on writes versus reads. Understanding which one is right requires understanding those trade-offs. Document partition secondary indexes are the simpler approach, and they're used by MongoDB, RAIAC, Cassandra, Elasticsearch, SolarCloud, and VoltDB. Here's how they work. When you write a record to a partition, the same partition updates all its local secondary indexes. Write car 1234, red, Berlin, 5000, to partition 2. Partition 2 also updates its local index for color equals red, its local index for city equals Berlin, its local index for price underscore range equals 20-30K. Only one partition is involved in the write. Writes are fast and local. Reads are where this approach struggles. When you query find all red cars, no single partition has a complete answer. Partition 2 knows about its red cars. Partition 5 knows about its red cars. Partition 8 knows about its own. To answer the query, you have to query all partitions simultaneously and merge the results. This pattern is called scatter/gather. Scatter/gather reads are expensive. They add latency proportional to the slowest partition. If one of your 12 partitions is temporarily slow, every secondary index query waits for it. They generate load on every node in the cluster for every secondary index read. At large scale, scatter/gather can become a significant bottleneck. The book is direct about this. Queries on secondary indexes in a document partition system can be expensive. This is a fundamental design limitation, not a bug. The architecture makes writes fast at the cost of read efficiency. MongoDB's user-facing documentation for this scenario actually says, query performance can suffer if you must scatter/gather across many shards. The database acknowledges that this is the cost of local indexing. For applications where secondary index writes are frequent and secondary index reads are rare, event logging, time series data, audit systems, local indexes are the right choice. For applications where secondary index reads are the dominant pattern, product search, user discovery, the global approach is worth the right complexity. Term partition secondary indexes take the opposite trade-off. They make reads efficient at the cost of write complexity. In a global index, the index itself is partitioned separately from the data. The index maps terms, color equals red, city equals Berlin, to the locations of all matching primary records across all partitions. When you query find all red cars, you hit a single partition of the global index that owns the term red, and that partition returns the IDs and partition locations of all red cars everywhere in the cluster. One index lookup, no scatter/gather. Why not just keep the entire global index on one machine? For the same reason you don't keep all your data on one machine, it can't scale. Instead, the global index is itself partitioned, typically either by key range, so color terms from A to M go to one partition, N to Z go to another, or by hash of the term. The catch is on writes. When you write car 1234, red, Berlin, to partition 2, you now need to update the global index entry for red on whichever index partition owns that term, and the global index entry for Berlin on whichever index partition owns that term. Those index partitions may be on completely different nodes than your data partition. A single write now involves multiple partitions, potentially multiple machines, and coordination between them. This is why global secondary index updates are almost always asynchronous in practice. DynamoDB, for example, documents that its global secondary indexes are updated eventually, not in the same transaction as the primary write. That means a write to the primary data can be immediately visible, while the global index hasn't yet reflected the write. A secondary index query run immediately after a write might not return the newly written record. The choice between local and global secondary indexes maps cleanly to the application's access pattern. Write-heavy workloads with occasional reads favor local. Read-heavy lookup workloads favor global. Many systems offer both, letting you choose per index.